basically estimating this standard deviation. So that's a distinction between t-tests and SAT tests. SAT tests, you have the standard deviation given. So moving forward now for that midterm, you will only get standard deviations from the population. These are given. Moving forward for the finals, you will need to calculate them from your sample, and you're estimating your standard error of the mean from an estimated standard deviation from the sample, rather than have a given standard deviation. So understand that there are different types of variables. You have discrete variables and you have continuous variables. You can convert and transform continuous variables into discrete variables, as we have done in the frequency distribution chapter. You can hypothetically also, you can try to get discrete variables in some certain fashion with ordinal variables from a group frequency table. For example, you can try to make them continuous again, but it's not really something you would practically do. Continuous can take a full range of values. Basically can take any values within defined ranges, whereas discrete variables are basically predefined specific values. There you have nominal and ordinal, and for continuous you have discrete and ratio. And we're getting to the cookie example, which illustrates that quite well. Then we've talked about the Stroop test. Remember the Stroop test? That's not relevant right now. So we have two types of observations. So we have nominal and ordinal. Nominal is a category or a name. Ordinal has some implied ranking. Again, don't forget that example from the sample quizzes, which we have discussed for the bed. What was it? California size and king size bed and queen size bed. So there's an ordinal, an order to that variable of the bed size. But if you rank them according to the number of beds sold, then it basically takes a nominal. So understand this distinction. When is it a nominal? When is it an ordinal variable? Two types of observations can be continuous. We have interval and ratio. Interval equally spaced can take any value within a defined range. Ratio is like an interval but has a meaningful zero. The example here, name of the cookies, ranking of your favorite cookies. Interval is the temperature of the cookies, which has a meaningful zero, right? No, it has no meaningful zero. It basically can take up any value, can also be negative. If you freeze cookies, then they become negative, right? Ratio is how many cookies are left, which has a meaningful zero, because you can't, otherwise you could owe cookies, but that's not a practical example. Quantifying, so you have a different occurrence of these. We have discussed that in detail. And now we're coming to the more general terms. And this is why this chapter 1 is actually quite important, because you have 3 different types of variables that you will face. You essentially, the third one is actually, there are more to those, but these are the 3 principal ones that you need to understand. You need to understand, and I'm starting with the dependent variable. The dependent variable is your outcome variable. So if you have a correlational analysis and you want to kind of see whether athletic performance associates, and this was the example we're going to discuss, we have discussed, if you want to see whether athletic performance with whatever metrics associates with the number of hours of practice you've put into practicing that exercise or that sport, you basically have athletic performance being the dependent variable, and the hours of practice is your independent variable. So this is basically the modifiable variable. And the dependent variable is the consequence of that. Now you have on the pathway, you have confounding variables. That's basically the third variable. Whether somebody is athletic when he or she started that exercise, when he or she started that sport, would be a potential confounder. Somebody being, I don't know, not strong enough, the muscles are not built up in a way that they would be good at that sport yet before they start exercising. These are all confounding variables, right? Like athletic performance at the start of the observation period, when he or she starts exercising that sport. So that would be a typical confounder. Independent variable would be hours of practicing the sport, hours of exercise. You have to distinguish, you have the distinction between reliability and validity. A reliable measure is consistent. That means you measure the height of a student on Monday. In a perfect world, that height would still be the same on Friday. So it's a reliable measure to measure the height of a student using a valid meter to measure the size of the students. So the measuring tape should be accurate in measuring the height. If it's not, then it's not. Then it's not a reliable measure. So a good variable would be reliable and valid, meaning that the measuring tape is accurately measuring the height, and it can be reproduced the day after or a week later, and it still gives you a reliable measure. Fact is that, and this is now outside of the scope of this, essentially they are not really valid measures. So every laboratory parameter, every measurement essentially has an inherent variability. So if you go and get your cholesterol checked tomorrow by your PCP, and it's going to be measured again a week later, it doesn't necessarily mean it's the same value, because there's a certain measuring variability to it, which complicates the entire conversation, obviously. So in terms of validity, we talked about the Rorschach ink blot test. Both reliability and validity is debatable, but let's not go too deep into this topic. Hypothesis testing we have done in much detail in chapter 7. You're basically trying to draw inferences out of your data. You have a dependent variable and independent variable. You try to draw inferences that basically gives you an idea of a conclusion to be drawn from that data. And you're trying to convert it in a binary interpretation. Yes, no. Is the mean of my sample different from the population mean? Yes or no? Yes. At an alpha level of 5%, I conclude that this sample mean is different from the population mean. That's what hypothesis testing essentially is. You convert data into an insight that is binary in nature. Yes or no? What's important in this context is that you have operational definitions. You need to understand how to convert a research question into a dependent and independent confounding variable. You need to look into, at the research question, and this will be definitely something you will face for the midterm. You get a research question, and you will need to understand what's the dependent, what's the independent variable, what could be a confounder. So practice the questions and the sample quizzes from that angle. Try to think deeply about what is here, the dependent, what is the independent variable. And you have, in the book, you have plenty of examples as well. So just understand the operationalization. So if somebody tells you like, yeah, I have a pet, and since I have a pet, I'm happy, and I think that's for everybody in the population like that, understand that the independent variable has pet ownership, yes, no. And the dependent variable is the level of happiness. That's the consequent. So whatever can be modified is your independent variable. Everything that can be manipulated. Excuse me? You said everything that can be manipulated is a different. No, everything that is manipulated is modifiable in a way is essentially your independent variable. And this would, in this context, so independent variable and dependent variable becomes very obvious in correlational studies. And here's the slide. No, that's wellness. Okay, health behavior, high level of health behavior, use of a wellness program. On such a scatter plot, you will always have the independent variable on the x-axis and the dependent variable as the outcome on the y-axis. So whenever you look at a scatter plot and you're being presented a scatter plot, y-axis, the ordinate, is your dependent variable, and the abscissa is your independent variable. It's also essentially you can quantify that trend, and we will do that with regression. We're predicting the outcome based on the independent variable. So this is a correlational study. If the independent variable were just a binary variable, or for example, like use of a wellness program, no. Use of a wellness program, yes. And it would be a dichotomous variable. You only had two levels. And the difference here would be quantified. So this independent variable would basically only give you like 2 outcomes, which is 2 means.
That nominal?
That would be a nominal variable, yes. And so what we do with the STAT test essentially is a comparison of a variable to a second variable, right? It goes in that direction, but later on we will compare groups, mean of groups, that essentially will make this more obvious. Types of research design. So we basically have an experiment. An experimental design is where you place an intervention on your sample population, which is blood pressure medication, exercise programs, health behavior changes, whatever intervention you could think of. And you are facing here the problem of confounding. Think of the exercise example. You have a high level of exercise in the beginning, whereas in the other group, there's a small fraction of subjects that have a high level of exercise. That's a confounder. This proportion of exercising students would be a confounder in your comparison, because it would inform your outcome without you actually having it in your group allocation. This is why you do random assignment in studies. You mean to equally distribute these confounding variables. So you have exercise program, yes, exercise program, no. Only with random assignment, you get an equal proportion of highly motivated, highly exercising students in both groups. And you want this proportion to be identical or somewhat comparable. So that's why you do randomization. With randomization, and here's the example that Nolan and Heinzen gave. So you have employees that are assigned to have access to wellness program. This is how you essentially get an equal distribution of these health behavior seeking individuals. If you have them self-select into these groups, you get a larger proportion of health behavior or health behavior modifying seeking participants in that group that you actually want to study. So obviously this will be a biased result. So this is then a confounder in this analysis, which you couldn't adjust away. Understand in the very same topic also the difference between a between group design and the within group design. That I'm flagging this because that will come quite often, and there was some misunderstanding I've noticed in the past, and that's a pity, such a misunderstanding. Between group is you have 2 groups and you follow these 2 groups and you compare these changes over time. Within group, you have 1 group, you follow them over time and you observe their changes over time. And we will do the statistical tools to essentially test these both examples through. But understand between group and within group design. To some extent, it's self-explanatory, but it's important to keep in mind and have thought about it once. So data ethics. So these are basically ethics that come to design, data collection, analysis, interpretation of analysis, and the reporting. So there are rigorous rules essentially to all aspects of these. So research design follows certain outlines of studies. These need to, obviously research design needs to go through an approval of an ethics committee. Every study that is being conducted will be reviewed by so-called IRBs, institutional review boards, that look at all these proposed studies and will give an ethical okay to them. Data collection is also important that it's being done diligently in a transparent manner. Analyses need to be reported and conducted in a transparent manner. Interpretation needs to really reflect the data at hand and the analysis being done and the results being seen in that way. And the reporting is another topic which becomes more and more pushed in the spotlight nowadays. You need to basically follow guidelines for whatever research you're publishing. You follow a very rigorous outline of how you're reporting data and how you're reporting your research results. Open science is then the next level of data ethics, where you make your research very transparent. That means you're showing exactly what you did, how you did it, you report it diligently. You give also access to data. In many cases, many journals ask for access to data. However, there are still problems with science, with research. Problems are replication failures, problems with data collections, which is always a problem, particularly in psychological research, and old-fashioned statistics. One. Pre-registration, you register your studies. If you have interventional studies, you will register them, and there are governmental registries that basically allow you to register those studies beforehand. You predefine where you're going with your research, how you analyze your data, how you will report your data. And this just makes sure that you follow exactly what you said you would be doing before you even start the study. That's becoming more and more important. And it is meant to prevent harking, which is hypothesizing after the results are known, which leads to a type 1 error, because hypothetically could lead to a type 1 error because you may be looking at things in a way that you're more likely to get a significant result. So that's chapter 1. These are the bullet points. Understand in broad strokes what all these things are about, that you recognize them in the questions. Then we had chapter 2, the frequency distribution. It was a simple chapter. Think of the volcanoes. You're basically transforming your continuous data now into discrete data by basically depicting your data as frequency, your continuous data into discrete data. So you're discretizing continuous variables. You build frequency tables, group frequency tables, and frequency histograms. Distinguish the raw score. Well, we know all of this. Remember the volcano example. It's basically we have then grouped the countries, the number of countries with a certain number of volcanoes in them, basically led us to the frequency tables. And with the idea then that a histogram is a way to depict the distribution of the data and each individual score of your data. And the histogram is really which basically leads then to the understanding of a so-called frequency polygon, which leads to the normal distribution, which basically is, as we know, a mathematically defined function that basically covers our 100% of the population, from minimal entry to maximal entry. We have 100% of the population in there, and we can then standardize them, which we're going to get to with the SETS course. Understand normal distribution and skewed distribution. Please don't mix up left skewed and right skewed. The direction in which the tail is pointing is the direction in which it is being skewed. If it's right skewed, the tail is pointing to the right. If it's left skewed or negatively skewed, it's pointing to the left. It's not difficult, but sometimes.
We go back, then I just want to see which.
Well, it comes here. This one. So that's a positive skew, points to the right. That's a negative skew, a left skew, points.
Which one has the ceiling and the floor?
Well, a ceiling effect would be, so if you have an exam, and you will see my graphs once we did our midterms, because I'm doing my graphs, and then I usually share them with the class. So if you have a maximal score of 100%, which is 200 points on the midterm, if a majority of students basically reaches 100%, you have a flooring effect, not a ceiling effect, because there's a ceiling to that data. So you get a ceiling effect. If you have a really good class, you get a very distinguished, clearly cut ceiling effect, which I hope to see next week. Yeah. If you have a flooring effect, you have a really not so good class, and you basically have a lower limit. Same principle. So you have a majority of people or students on the lower end. So if there are cutoffs, then you get flooring and ceiling effect. Dot plots, basically individual entries being showed as dot, not really commonly used. I have maybe seen a handful in publications, so it's rather a rarity. So that was a simple example and a simple chapter. Just understand the basics of it. The shapes of the distribution, I think this is quite something that you should make sure you're solid on. Then we have the visual displays. That's a little bit more involved, and you will get graphs that you need to interpret. You will get graphs that you need to kind of describe in some shape or form. And there's essentially, this is to be read up. Understand these lies: bias scale lies, sneaky sample lie, interpolation lie, extrapolation lie. Understand the differences between extrapolation and interpolation. So extra is outside, inter is in between. So when you interpolate between 2 points that you have inaccurate values. Scatter plot, understand the scatter plot, but you've all done it for the homework. Yes. The honeycomb, or the cockcomb. This one? Well, so this graph essentially has shown every month of a particular year and shows in its radius essentially the proportion of deaths from a certain cause. So it shows not only the proportion, but it also shows the actual counts. So you see, for example, as in January and August, you had the highest number of deaths, and you basically also see a proportion of causes of death.
So it's a few different values and like a lot of different.
It's a lot of information in one graph. Yes. So there are graphs like that. You see them nowadays. What's quite popular is a so-called radar graph, where basically you have like individual points and you kind of compare them, and it looks like a radar screen. This one I've never seen outside from that textbook. I've never seen that graph, but it's 150 years old. So, but basically it shows the counts, the proportion, and you can, based on this proportion, you can kind of see, okay, when did most people die, which was in winter, which is not surprising because in winter you have all kinds of diseases. Back then they didn't have antibiotics. It's a great problem. Then they had also, in addition to that, they had some war that basically ended here in November. Then you have those people that survived the war, but then kind of the immune system was definitely not the best. So they basically caught then some form of diseases and they died then moving forward. So it's a lot of information in one graph. Yeah, that's pretty much. No, please. No, it's a fascinating graph, right? Particularly because it's historic data, and you may remember from the first slides that I've shown you, there was the pestilence in New York City, also from the 1860s or so. These were the first attempts to really use descriptive statistics and use the descriptive statistics to gain insight into disease patterns and disease dynamics. And so the birth hour of epidemiology, so to say, was a physician named John Snow, who basically determined in London the cause of acute diarrhea, of which many people died, which essentially was caused by a cholera emitting well somewhere in South London. And he was basically able, with descriptive statistics of a certain area, so he used a map, and he basically was able to identify the upstream area from which that well basically drained the water to, and people would drink that water, and he would basically be able to identify that well as being the source of this cholera containing water. So these are the first attempts to really kind of make sense out of data. And this is just, the 19th century was really the birth hour of epidemiology as we know it nowadays. And these are also, this goes in the same direction. It kind of, it shows the year of interest, how things basically changed. And it has some timelines even. It shows here the war in Crimea basically where death rates then increased as a consequence of violent battles and violent conflicts. So scatter plots are great because they basically show each individual point, understand the difference between a linear and a non-linear relationship. It's usually easy. So the examples you will likely see in your quizzes are easy to interpret. They should be easy to identify, easy to interpret.
Linear and non-linear relationship.
Linear and non-linear. So basically, the way you would look at this, if I place, so we've done the trend line, if you remember. You put the trend line through a scatter, and it takes a linear shape, and it kind of seems to capture that trend quite well. So if I put a line through here, that kind of will capture that trend.
It's
then
also like scattered.
It is quite scattered. So, and we will come into the metric how to quantify that scatter. Yes.
What is it nonlinear?
Nonlinear would be when you put a nonlinear function through and it basically starts increasing here at the end. That would be.
That could be scatter plot. Most scatter plots are only, you just do the best fit line.
Well, the best fit line, yeah, but the best fit line doesn't have to be a line. It doesn't have to be a nonlinear line, right?
Oh, it doesn't have to be just.
There are nonlinear lines that you can fit through. Yep. So there are basically different ways how you would do that. So one way how you would do that, you remember how we calculate the standard deviations, right? So we take the deviations from the mean and we're squaring these deviations and then we calculate the sum of squares. One way how you would fit that line is with the so-called least square approach, where you quantify these squared distances between the individual points to that line. And you find that line of the least square between those individual points. That's the most common fit. That's also the fit that Excel is using. You also have a maximum likelihood fit, but that's a different conversation piece. So, but basically you find just that particular line that fits with the least deviation from the individual point to the line. And that can be linear or nonlinear, and that can be quantified. Okay, creating a scatter plot, we don't need that. Linear, nonlinear, we talked about this. Line graphs, line of best fit. Yeah, these are time series plots, but time plots, time series plots, it's actually a time series where you basically have on the x-axis as the independent variable, so to say you have time, and you basically see that dynamics over a certain time series or time plan.
So time is the independent variable?
Time would be here the independent variable, yes. Then you have bar graphs and Pareto charts. We talked about that. Bar graphs, basically nominal variable as the independent variable. Percentage of internet users would here basically be the dependent variable. Unordered, alphabetically ordered is here the bar graph. If you order them as per the magnitude, it becomes a Pareto chart.
Is it from least to greatest or like highest to lowest or lowest?
Highest to lowest, either or. Both is Pareto. So bar graphs highlights differences. You can deceive with the scale by taking the scale off. You can distort data with pictures. Know the different types of chart chunk. So you have the moire vibrations, you have the ducks and the grids. Don't use those. Never ever look at a pie chart and complain as soon as anybody presents you with a pie chart. It's an absolutely inferior way of depicting data. So basically know which graph you would choose on which variable. So if you have one scale variable you want to just display as a frequency graph, right? Displaying the frequency. You do a histogram or a frequency polygon. Well, the frequency polygon is just the mathematical function depicting that distribution from the histogram. If you have one scale independent and one scale dependent variable, you do a scatter plot, or a line graph only do when these values are associated. So in a time series plot, then do a line graph. If you do a regular scatter plot, do not connect those dots. Just don't.
You already know that there is a correlation between that.
Well, if there's a correlation and you want to show the relationship, you can make a line through it. Yes, a trend line or a fit line, but do not connect the points. So this is what they mean with a line graph. They're basically all the points are connected with each other. And a time series plot, you can do that, but in a regular scatter plot, don't connect the dots. One nominal, one ordinal variable, bar graph or Pareto chart, or if you have a continuous variable and you want to also express the variability around it because you have a standard deviation and you want to depict confidence intervals, you can also do a so-called box whisker plot. If you have two or more nominal, you do a bar graph or again a box whisker plot. These are the chart chunks, future graphs, multivariable graphs, bubble graphs. You've all seen Hans Gosling's presentation. graphs where you depict individual data points are always to be preferred over bar graphs. I personally don't like bar graphs much because they take this information out of the equation. You don't see the individual point anymore. A violin plot is a nice way to actually show that. Here on the inside, this is a box whisker plot. Know how to interpret it. So this is basically, this is the median. Stratifying the data in less than 50, in the lesser 50% and the upper 50%. You have Q, you have Q1 and Q3 basically shown here. You have here the lower 25%, in between here the 50%, and here you have this is the 75th percentile. So this is the 25th to the 75th percentile. These two whiskers contain 95% of all the scores. That's basically Q1 minus 1.5 times the interquartile range, or it's upwards, the whisker is Q3 plus 1.5 times the IQR. So, IQR, the interquartile range.
Why do you use 1.5?
But because it captures altogether 95% of all the scores.
So why is that 1.5?
1.5? Well, yes, because that way it captures 95% of all the scores.
How's 1.5 95%?
Yes. 1.5 times the IQR plus the Q3 will capture 95% of all the scores because of the distribution, the rules of the distribution. Violin plots are basically also showing them the distribution, and that's why they're a good way of depicting data. Good, that was the visual displays chapter. We're going to number 4. Central tendency, that's a simple one. You will not, well, in case you have to calculate a standard deviation, I will highly suggest Excel. Know in principle how to do it. STDEF.P. Yeah, no, STDEF.P.
Are groupies always be asked population, or would it like specify sample?
Well, if it comes to a T distribution, it would be STDEF.S or STDEF as a general function. It's the more common way of looking at data. STDEF.P, the difference is that you don't have that n-1, which we will start talking about on Wednesday.
But then on the test, we would mainly, like on the homework, we use STDEF.P.
Correct.
And that's what we would use also.
On the midterm, yes. Yes. Okay, understand in principle what mean, median, and mode are. Mean arithmetically derived as the sum of all individual entries divided by the count. Understand the difference between statistical parameters, so you have M or X bar, or you have in the population as a parameter, you have mu, M or X bar mu. Know the median, know what it means, less of 50%, higher part of the 50%. Know how to calculate it, know how to identify it. This is probably something you will be facing, identify the median out of a number of values.
Makes the lineup, right?
Yeah, you have a couple of numbers lined up, and you will have to identify that one
Do
median.
we have to reorder it first? Or will we-
You will have to order it, yeah.
Do we
Yeah.
use Excel for that?
Except, absolutely.
How do we do the mode on Excel? How do we do the mode on Excel?
Well, there will be no mode estimation, and the mode will possibly
Median, sorry.
or median. Well, just the way we did it in class, right?
I don't remember calculating the median.
Well, lecture recording.
Okay.
It's easy, just find the middle score. And if you have an even number, you need to take the average of the middle two values. Know the differences between unimodal, bimodal, and multimodal distribution. Yeah, like here, for example, the distribution of violet. That's the cherry to navigate. Understand outliers and understand which flagging this. Know which of these markers of central tendency is more reactive to an outlier. If you have one outlier and there, what reacts more, the mean, the mode, or the median?
Me,
Correct. Why?
because. So awkward.
Okay, one of you has to say that. Exactly. Yes. So it's an arithmetic relationship that basically will react because you're adding it to the sum and then you're dividing it by the same count. Yeah. So outliers are super important, and if you exclude outliers, you need to understand why you exclude them, and this needs to be understood and justified. So mean, median, mode, yes, variability, measures of variability, know why we do variability, why is that actually so important to understand variability. And these distributions, you have a range, you have a variance, where the variance is basically the average squared deviation. And if you divide the variance by the number of entries, you're down on the level of a squared deviation if you take the square root. Range easy. First quartile, Q1, Q2 is the median, Q3 is 75th percentile. Understand the distribution, understand the percentile, because that goes in the direction of standardization already. This is all interrelated, and that's what I meant, it's interrelated. Median, subtract the mean from every score, standard deviation. Again, parameter versus statistic, understand the distinction, and understand how to interpret them. Good. Central tendency and variability. Any questions so far?
This is great.
Thank you. I'm happy to hear that. I'm happy to hear that. I think that's why you.
I want to like review the later material because that.
Yes, yes, we're getting there.
So this is for, sample because there's no Greek letters?
The sample statistic are no Greek letters,
So
yes.
that would be, or does that count? Does this not count?
An SD would be a statistic, yes.
A sample?
Yes, it would be a sample statistic. It's a concept at this point. We're not yet at the level to really estimate it. So if we are calculating what we did is actually not how you would really use that. Usually you would use the STDEF because you're dealing with a sample, right? And that's why you would calculate the difference. So this n here would be subtracted by 1, and you would deal with so-called degrees of freedom, which we're going to get to on Wednesday. We're not doing that now. So I put thought into cutting the midterm exactly at this point because it's a little bit of a transition, which we're going to do on Wednesday. Okay. So sampling and variability. This is a more general chapter. But it's important to understand because essentially we are sampling and we need to understand what that actually means to sample. So we need to understand the random sample and convenience sample and also how it's not a quantitative term, but how impossible it actually is to get a purely real random sample. Convenience samples are being drawn because it's an accessible population. For whatever reason, it's more convenient or feasible to actually to sample this population. So sample is already available. The problem is you're sacrificing generalizability. Potentially, you're sacrificing generalizability
With convenience sample.
with a convenience sample. And the synonym for generalizability is external validity. You distinguish external and internal validity. External validity is the generalizability of a sample. Is that statistic I'm doing on that sample actually representative of the population? Internal validity is, do I have a confounder in my comparison? Is my comparison actually being designed and conducted in the right fashion? So this is internal validity. Volunteer samples, self-selected samples, we talked about it was the health behavior, crowdsourcing, online Turk, bias samples, testimonials, don't trust them. Random assignment to take out the confounding. Random selection would be also something that you could do, but it's harder to do. What you do is sometimes you do stratified selection, so stratified recruitment. that you have a preponderance of non-diabetics, and then you just focus on recruiting from diabetics to kind of mitigate the bias you have in your sample. Probabilities, understand how to calculate probabilities. You roll it I1 once, and you have a 1/6 probability to have a 6. The second time you still have the same probability because it's still the same die. You multiply these two mutually exclusive probabilities to get to the probabilities of having 2 6s in a row. Personal bias, confirmation bias are preconceived notions that you basically see confirmed. You have illusionary correlations. Running faster on a marathon, if I were the talisman my grandmother gave me. Subjective probabilities, trial outcome, yes. So frequency probability becomes important because if I have a population of the city of New York, there's a prevalence of 10% of diabetics in New York. I randomly pick an individual in New York. I have a 10% chance to pick a diabetic in a perfect world. If I do this 1,000 times, I will likely still have 10%. So if I have a 10% probability, and this is what the law of large numbers is, if I sample a large number of individuals from a population, I will essentially get samples that were the prevalence of all my samples will resemble the prevalence of that condition in a population.
Like the mean of the sample should be. Like
Not the mean, proportions. We're talking now about probabilities. You have a probability of 10% to pick a diabetic. Your sample number 1 is 100 people. Out of these 100 people, with a probability of 10%, you should have 10 diabetics in there. Likely you will have not, but you may have only 9. If you take now 100 different samples, higher sample sizes will be more likely reflecting the proportion in the population. They may not exactly, but they will if you do 100 samples and you get 100 different estimates of that proportion in the population, you will actually get individual entries that form again a normal distribution. And this is the law of large numbers. You can essentially, with proportions,
how are you having the normal distribution?
Well, because you get 9, 10, 11, 12, 9, 8, 7. So you get different estimates of the population. And this, exactly, but they all will basically gravitate around a mean of 10% again, because that's what the proportion of the population is. So it's the same concept as with our random samples, and we have the distribution of the sample means. Now it's a distribution of the sample proportions. And you essentially, can, if you deal with proportions, and we're not doing this in this class, you can actually use a normal approximation for calculating and dealing with proportions. So you build a variability around the proportion, and you're calculating confidence intervals, and that's how you can compare proportions in samples. We're not doing this in this class, but yeah, it's one way to deal with it. You will hear it again in further statistical education. Probability successes over trials. This is my 1/6, and these are the 6 different possibilities that STAI could possibly roll to. So it's 1/6. Confidence is a personal probability, is a rating of our confidence that this event will occur. 95% confidence intervals, we are 95% confidence we are capturing that population mean. That's what this is referring to. Inferential statistics, rules of probability to test for hypotheses. So we are transforming our sample, the data from our sample, into a dichotomized decision. We're saying yes or no. Is our null hypothesis correct, and is our sample mean identical to the population mean?
But discrete.
We're discretizing, well, no, it would be a mean from continuous data, comparing it to one population mean in our example now. So the hypothesis is basically, the null hypothesis, like sample mean equals population mean. If we are at a p-value less than 5%, so the probability of this being true is less than 5%, then we will reject this null hypothesis and accept alternative hypothesis, which is basically making a binary statement. It's not different if it's significantly different. Yeah, and here we come. So that's exactly what I was talking about. So there's no difference under the null hypothesis. There's a difference under the research hypothesis. We have control groups and experimental groups. Are the means different? This is the analysis which we do with two different samples. That's moving forward, which we will do. We're rejecting the null hypothesis that there's a difference. We fail to reject it if there's no difference. Good, we know that. We have a type 1 error and a type 2 error. We'll talk about this again with power. Type 1 error, we're rejecting a null hypothesis when it's true. Although we are with a type 1 error rejecting something where the null hypothesis would be true. So there's no difference, but we are rejecting it because we used a subset, or we excluded some outliers. We're rejecting something we should not have rejected as a type 1 error. We failed to reject something that should have been rejected as a type 2 error. Again, remember statistical power. You have a null hypothesis that is true, a null hypothesis that is not true and should have been rejected. This probability should add up to 100%. You fail to reject it, that is your better. That's your type 2 error. And then you basically have statistical power, that's your 100% minus the type 2 error. In the opposite, you have the type 1 error, you have your the type 1 error, again, you're adding up to 100%. You are rejecting something that you shouldn't have rejected, that's your type 1 error. You're not rejecting what you should have rejected, that's your leftover correct decision, which also resembles in the knowledge of a predefined alpha, your confidence interval. Right? And the shocking prevalence of type 1 errors we talked about, that's a 1.96 increased occurrence of reports that contain the 1.96 SAT score, which is corresponding with a p-value of 5%. Is more likely because there's a because of publication bias, which is a bias where researchers are more likely to report results that are significant. There is a tendency of type 1 errors, hypothetically, where researchers kind of strived to get the result somewhere below a p-value of 5%, which corresponds to a SAT score of 1.96. Consequently, there's
equals 0.05 is also C equals 1.96.
Correct. You remember the 2.5% tails on both sides, right? That's minus 1.96 and plus 1.96. Good. Next. Good. Chapter 6. Normalization. That's an easy one. The normal distribution curve, unimodal symmetric bell-shaped, has one mode, is at the mean 50%. Since it's symmetric, you're 50% less than the mean, 50% above the mean. It's not skewed. Yeah. The larger the sample, the more likely it's normally distributed. Standardization is basically standardizing your normal distribution curve according to standard deviations, where between mean, where set equals 0, and standard deviation of 1, you have how many percent? How many percent of the population is between the mean and one standard deviation?
Oh, 68.
Between set equals 0 and set equals 1. 34.
I said 34.
You said 68.
I said 34.
Okay, then you were right. Okay. So also remember the empirical rule, 68, 95, 90, 99. The rule of
One standard deviation is only from like 0 to 1.
Yeah, that's the tricky part. So you have between set equals 1 and set equals minus 1, you have 68%. That's two standard deviations.
But if you just went from -1 to 0, that would be
No, that's also 31, 34.
34.
So there's 34 and there's 34. Together is 68. Then you have 95.7 between two standard deviations, minus set equals -2 and set equals +2. And then you have 99 between 3, 6 in total on both sides.
Where's the number 5? Between
95 is -2 to +2. Yeah.
So the whole scale goes from -2 to +2.
Yes. 68, 95.7, and 99. Good. Standardization, x minus mu divided by sigma gives you the number of individual scores. Characterize it, standardizes your population. Okay. Why do you do that? Because you want to compare apples with pears, and you can also calculate back by just rearranging the formula by calculating set multiplied by standard deviation plus the mu gets you to the individual x. Why does this formula look familiar? Exactly, it's just a rearranged formula, but remember how to calculate confidence intervals. It's the same thing. It's the same formula, you're just replacing that set with 1.96. So it's the same concept employed here. That's what the calculation of the confidence interval is. You're just rearranging the formula. So you are comparing apples with oranges.
Z-scores compare what? Where you said something about the Z-score.
No, the C-square. So what you have with the C-square, this is the same formula as we're using for the calculation of this confidence interval. We have mean minus 1.96 multiplied by sigma, or the standard error of the mean, gets you to the lower limit. The upper limit is 1.96 plus that mean. Right? So it's the same concept. And you're taking the set score despite being in, okay, that's it. In the t-distribution, you would also use a set score after a certain sample size. So set scores, you use this as standardization to compare apples with oranges or different emotions, like here. You can transform them into percentiles with the set score table. You all know how to read the set score table by now, so that should be simple. That's the empirical rule. These are the percentages we talked about before. And now we're getting to the central limit theorem. The central limit theorem is basically bringing this now into action and moving towards hypothesis testing. So now we're trying to convert our standard deviation and the variability from our population into the distribution of the sample means. So if I draw repeated samples, my means will distribute in a certain way and will have a certain variability. And this variability is related to the sample size and to the standard deviation in the population. So the more variability in the population, the larger the variability of my sample means is going to be, which affects then the set score for my hypothesis test. But generally, if you create, okay, so you create a distribution of the sample means, it's going to be skinnier, more likely normally distributed. And that's also the reason why you can use the same parametric tests that basically have as the basis assumption a normal distribution. You can also employ this on non-normally distributed data, because if you sample and you look at the distribution of the sample means, even if the population is not normally distributed, the distribution of the sample means will be. That's why you still can use parametric tests. But basically, it comes to two main things. So one is that the mean of the sample and the mean of the population is identical. You are relating that sample mean under the assumption that you're randomly sampling.
It's not identical.
Well, that's what you're testing then in the hypothesis test, right? But you're randomly sampling. You assume that your sample mean is identical to the population mean. And secondly, the distribution of these sample means are distributing around that mean of your sample in relationship to sigma, which is the standard deviation of the population, and the square root of the n, the size of your sample. Because the larger your sample, the more likely you're going to have an identical sample mean that is identical to the population mean. And the less variability you will have, because you have a more accurate estimate of your population mean.
So before with the 10 people, right? That's like what you said before with the 10 people.
Same thing, same principle, but there's a proportion. There's a proportion. Now it's mean. Same principle though. The larger your sample, the more accurately you're estimating what you mean to estimate. So that will affect the standard error of the mean, which is the variability of these means, and that basically will inform your hypothesis test. Scores versus means, yeah. And now we're calculating, now we're standardizing our distribution of the sample means according to the mean minus our population mean. So we're calculating a difference, individual differences of all these samples that you have drawn, and you're standardizing these differences. And if that exceeds a certain critical value, then you're rejecting your null hypothesis of the sample mean being identical to the population mean. And this is where the cheaters come in. Yes.
Can you explain this when you use the standard error of the mean?
So the standard error of the mean is the standard deviation of the population, the variability of the individual scores in the population that is given to you for a STAT test, divided by the square root of the n. So if you have a lot of variability, your distribution of the sample means will also be wider, because there's a lot of variability in your population. There's a lot of noise, right? If your sample is small and your denominator is going to be consequently smaller, your variability is also going to be larger, because your estimate is not as accurate as it should be, or as it would be with a larger sample. So essentially, this is the relationship you're looking at. A lot of variability in the population, larger standard error of the mean. Distribution of the sample means wide. Small sample size, also more variability in the distribution of your sample means. Consequently, smaller set, because your standard error of the mean goes in your denominator of the calculation of your set score. And that's where this interrelates, right? So this is then the consequence. This is going to be larger if this value is smaller. So if there's less variability in your distribution of the sample means your set is going to be larger, and then you're more likely to exceed your, yes.
Can I just clarify something? So
Sure.
if you have a larger variability in the population and or small sample size, then this will create like larger variability of your sample.
Sample means, yes, correct. Yeah, correct. So this builds now, so we have 10 more minutes. Oh, well. So we have 10 more minutes now for a hypothesis test, and which we have kind of started already. For hypothesis test and confidence intervals. So we have what confidence intervals we add now. With the hypothesis test, we have okay, we know the set score table. You're basically meaning to transform your data into a binary outcome or insight. So you can still catch, we know all of this, the calculations, they're simple. Set statistics, you basically understand parametric versus non-parametric tests. For parametric tests, you have the assumption of a normal distribution. Both are inferential statistical tests. We are only dealing with one non-parametric test, which is the chi-squared test, chapter 16. Chapter 16 is the chi-squared test, the comparison of proportions, essentially. Then we have 3 assumptions for hypothesis testing using parametric tests, the STAT test. We have a scale variable as the dependent variable. We have randomly selected participants, and we have the distribution is normal. So these are the 3 assumptions. Flagging this, that's an important one. 6 steps of hypothesis testing. We talked about this. Identification of populations, distribution assumptions, choose the appropriate test. There, I'm quickly going to show this slide. Oh, come on. I'm quickly going to show this slide now. So we're dealing here. So this is posted in addition to this chapter. It's in Canvas. So we're dealing right now with only a one sample set test. We're not even a t-test, but these are the different methods that you will be using. So by the end of the semester, you kind of will be able to employ each of these for the purposes we have been discussing. That was actually not as relevant. Let's go back to this. Okay. Okay, critical values need to be determined based on your acceptable alpha. Test statistic is the set score that you're calculating, and then you decide based on the set score. Statistically significant does not always mean that it's actually relevant. We talked about this with very large samples. You will likely get significant differences, but it doesn't mean that it's really something that is relevant. You have a null hypothesis and an alternative hypothesis, and you need to distinguish between one-tailed and two-tailed test. Map it out, draw it out, look at the hypothesis test, those additional slides, the cholesterol example, which makes this nice visual depiction of what actually is being tested. That's just nice to keep in mind. One-tailed test is a rarity to be done. Parking, we talked about hypothesis after the research results are known. Then p-hacking is basically like subsetting until you finally find a significant p-value. But basically what you do, you standardize your distribution of the sample means, and if you see if you see a p-value that exceeds your significant p-value or a set score that exceeds your significant or your critical set score.
They're both not correct.
Hmm?
These are both wrong for this.
Excuse me?
These are both wrong, like you should.
Yeah, those you should not do. So hypothesis after research is known is like you pre-register your analysis and your research, and you will follow this, what you said you would do. If you then know the result, you have the data at hand, you're just like playing around until you find something significant, that's a big no-no, that's harking. And p-hacking the same, then you basically start subsetting until you find a significant difference. So that's not what you should be doing. And now quickly, this confidence interval for the last 6 minutes. So we talked about the example, the gender statistics, intervals. So the confidence interval is an interval estimate that basically allows you to describe an interval within which you're 95% confident to have described the population mean with. If your population mean for a set test is outside of this confidence interval, you're looking at the statistically significant mean, because the distribution of your sample means is basically within 95% probability not containing the population mean. So quantifying this allows you to do hypothesis testing as well. And it basically also, it's just again, like we discussed before, it's like the population size and the sample population size, so the sample size, plays into your estimate of the set score. Just because if you are dividing your standard deviation with the square root of the sample size, you get a smaller standard error of the mean. A smaller standard error of the mean here in the denominator will divide this difference by a smaller value. Therefore, you will have a larger set score, and you will be more likely to exceed your critical value, your critical set. Effect size basically allows you to quantify your mean differences or your differences independent of the sample size, because that sample size will be more likely giving you a significant result. So basically you put the weight back on the difference by basically quantifying the effect size. So as you can see, same difference here with a smaller variability because of a larger sample, for example, would basically lead to more regions that are not overlapping. So the overlapping regions are diminishing. As a consequence of that, they're more likely to be significant. So this is the effect size. quantified as Cohen's d, flagging this. There's a good chance you will need to calculate this and also categorize it according to the conventions. So Cohen's d is calculated as the difference divided by the standard deviation. And then here the conventional 0.2, 0.5, and 0.8, basically quantifying the overlap between these distributions. Effect sizes are being used to quantify meta-analyses, where basically you have then for studies, different studies studying the same topic, you can basically use one aggregated effect size based on various different effect sizes from different studies. In the simplest format, this is just a mean effect size. In reality, it's likely random effects models that basically are more advanced analytics and allow to incorporate the variability of each respective study. File draw analysis are analysis that basically estimate how many studies hypothetically ended up in a file drawer with a null result that would have brought your overall estimate of the meta-analysis to a non-significant result. Is sometimes done because it may be that replications weren't successful and weren't published. So it's quite a standard reporting value. Statistical power is basically, as we talked about, and this is the most important table. So think of this, type 1 and type 2 error. You have here 100% probability that you will either correctly reject or incorrectly reject the null hypothesis or reject the null hypothesis correctly. So the probability is 100% if there's no effect. If you reject it, it's a type 1 error. And the difference here is the correct decision, which would be alpha minus the 95% confidence interval. Then you have here, if you have an effect, you are not rejecting it because you didn't study enough subjects in your study. You designed it wrongly. Your power calculation was not good enough. You're basically running into type 2 error. Alpha, and this is beta. 1 or 100% minus that beta gets you to statistical power. Should be at 90%. 80%, most commonly, a rigorous design is 90%. So you can affect your statistical power by increase your alpha, not advisable because statistical reviewers are going to be quite opposed to that. You can also use a one-tail test. It basically expands the spectrum on one tail. Also not advisable, statistical reviewers will not like it. You can increase your sample size, and this is where you do sample size estimation in the context of a power calculation when you plan your study. Increasing a sample size will decrease the variability of your sample estimate of your standard error of the mean, and thereby will be more likely to provide you with more power in your research. Alternatively, you can also increase the differences between the means by intensifying your intervention if you do a prospective study. Sometimes not possible, so you're still stuck with essentially studying more subjects. But if you can increase the intensity of intervention by increasing a dose of antihypertensive medication, then this is one potential way to do that too. Sometimes, unfortunately, not possible and or practically not feasible or ethically not feasible. Good. Why do you need to know the study, the statistical power? Because by that you basically can design your research and do a sample size estimation. And that's all we did this semester in a quick cross section. All right, see you on Monday. Yep. Okay. Yeah, I would change it. Yeah. No problem. Yes.